I'm going to talk about black holes. I imagine that some of you are wondering what is the relation between black holes and star-forming regions and protostars. These are the main topics of research here. My answer is that whatever is born someday will die. And black holes are the remnants of some very massive stars. And very interestingly, they have some life after death. And this afterlife can be extremely violent. Actually, black holes are known to power some of the most violent and extreme phenomena in the universe. From microquasars, where a black hole is eating a companion star in a binary system, to gamma ray bursts, the so-called collapsars, where a supermassive star implodes directly into a black hole, producing extremely powerful jets that can produce more gamma rays in a few seconds than the rest of the universe. And, of course, active galactic nuclei, where we think there are supermassive black holes in the innermost part, powering the whole source. In my talk, I will focus on these X-ray binaries that were mentioned in the previous talk. And these are binary objects where we have a black hole or a compact object that is accreting matter from the donor star. Sometimes this is an early type massive star, so accretion proceeds by feeding through the wind, by the wind, and in other cases we have low mass stars, and then the accretion occurs through overflow of the Roche law. In any case, the basic elements of this kind of systems are the compact object, the black hole, the companion star, the accretion disk. This disk is formed because the matter has angular momentum, so it forms a disk around the black hole. Then the corona. I will talk specifically about some physical processes occurring in the corona, and in some cases, relativistic jets are observed in these binaries. When these relativistic jets are observed, we talk of a microquasar. Well, as I mentioned just a second ago, the matter has angular momentum, so when it goes to the potential well of the black hole, forms a disk. Then viscous dissipation of angular momentum in the disk makes the particles that are orbiting around the black hole to move to inner and inner orbits. And so the gas is hotter in the direction to the black hole, and very close to the black hole it could reach temperatures of the order of 10 million Kelvin. So at these temperatures the gas produces X-rays, and hence the name of this type of systems, X-ray binaries. Concerning the thermal spectrum of the disk, it can be obtained just integrating all rings, which have a characteristic temperature, each one of them. So the overall spectrum, in the case of a thin disk, is this kind of Sakura-Sunayev spectrum that is composed by the contributions of all disks. But this is theoretically, let's say, when we look at real systems, like for instance Cygnus X1, which is the best studied candidate, black hole candidate in the galaxy, the spectrum is quite different. We have a quasi-black body component that is originated in the disk, but we also have an extension towards higher energies. In this example, we see emission at 10 kilo electron volts, something that cannot be produced in the accretion disk. So the question comes about what is the origin of this high energy emission around black holes. One interesting thing about these objects is that the accretion disk is very likely magnetized, and since the field is frozen in the disk material, the motion of the accretion disk will produce a twisting in the lines of the magnetic field beyond what is called the Alfvén radius of the source, where the magnetic energy density is stronger than any other energy density. So beyond that point, the magnetic field is twisted, and this produces a kind of magnetic tower where there is pressure that can expel particles if we have some material above the disk. So essentially the idea is if we have plasma around the black hole and above the accretion disk, then the particles will be frozen in the magnetic field lines, and they will be expelled by a magnetocentrifugal effect. So the result of this is the production of these jets that are actually observed. And this is a case of the microquasar close to the galactic center, and this is another famous microquasar, SS433, whose jets are very well known. So if we have a plasma above the black hole, then this magnetocentrifugal effect can produce and collimate the outflows we observe. So the existence of the jet is a reason for thinking that this plasma should be there. So the name we give to this very hot plasma above the black hole is the corona. In this corona, not just slow evaporation in the form of an outflow can occur, but also very violent phenomena can take place. For instance, accretion can produce massive reconnection close to the black hole. This is the black hole. This is the ergosphere. This ergosphere is the region of space-time around the black hole that cannot be at rest seen from the infinite if the black hole is rotating. So when the matter is accreted in this direction, magnetic field lines are curved, and at some point magnetic reconnection can occur because we have the approach of different magnetic field lines with opposed polarities, so there is a sudden change in the topology of the magnetic field. So when the field recombines, it takes away part of the plasma that could exist above the black hole. And that can be seen from the Earth as the ejection of giant plasmoid. This kind of phenomena have been observed, for instance, by Felix Mirabel and Luis Felipe in microquasars in our galaxy, and the ejection is quite violent, and it occurs at relativistic velocities. Actually, if we project those relativistic velocities in the plane of the sky, what we measure is an apparent superluminal motion in the sky, but this is just an aberration phenomenon. Additional support for the existence of this corona around black holes comes from simultaneous radio, infrared, and X-ray observations of some microquasars. This comes from some observations of the same microquasar I showed in the previous slide by Felix Mirabel and collaborators. What is observed is a quick fluctuation in the X-ray emission of the source, and this emission is thought to be originated quite close to the black hole. The reason is that the variability is very, very, very rapid, so the size scale of the emitting region should be of the order of the event horizon of the black hole. But then the X-ray emission suddenly goes to zero, and a bit afterwards an excess of infrared emission appears. This is synchrotron radiation produced now not in the close to the black hole, but some plasmoid that is moving away with superluminal velocity in the plane of the sky. And if we measure the spectrum of this, we see that this is synchrotron radiation, while the spectrum of the X-rays is thermal. So these are two different components. Everything happens as if some part of the innermost part of the hot matter close to the black hole has disappeared, going into the black hole, and then just a fraction of that matter is ejected in the form of this non-thermal plasma. Now, if we have a look at the overall spectral energy distribution of those binaries, we see two dominant states. One is the so-called thermal dominated state, also known as the high soft state. Here we have a clear Sakura-Sunayev component. This is the accretion disk contribution. But then we have this excess of X-rays that can reach even gamma rays. And the other state of these sources is the so-called non-thermal dominated state or power law dominated state, or also called the Lauhar state. Here we still have the contribution from the accretion disk, but you see that now is much weaker than in this state. And we have this power law contribution up to energies of around 150 kilo electron volts. And even beyond that, there is some emission that can reach MeV, gamma ray energies. So what is the interpretation of this? The interpretation is that this is being produced by the accretion disk, but now in this state the accretion disk is smaller than in this state where the accretion disk goes all the way almost up to the last stable orbit around the black hole. And then we have a strong corona in this state that is also present here, but is not so strong. And this corona produced these hard X-rays by Comptonization, by inverse Compton upscattering of soft photons coming from the disk. So this corona should be formed by an extremely hot thermal plasma with temperatures of 10 to the 9 Kelvin. The disk has temperatures of 10 to the 7 Kelvin. And in addition, we have these two features here. We have this emission line at 6.7 kilo electron volt. This is iron K alpha line. This cannot be produced in the accretion disk because the temperature in the disk is not high enough. So there should be some source above the disk that produces the excitation of the line. And this source is the corona. And then we have this bump of high energy emission here that is interpreted as a Compton reflection feature. It's a radiation from the corona that is reflected in the accretion disk, producing this bump here. And concerning this ultra high energy excess, its nature is unknown, and it will be the main focus of my talk. So the whole situation is something like this. We have the black hole, the accretion disk, soft photons are produced here. We have very, very hot plasma around the black hole, so these soft photons are upscattered at high energies in the corona. The maximum energy for these photons is around 150 kilo electron volts, but we can measure MeV photons, so something else is happening in there. This is again another picture of the situation, but now in what is called the high soft state. We have the accretion disk, strong component here, but there is still a corona, an iron line that can be observed here at 6.7 kilo electron volts, and then we have the Compton reflection feature. There are transitions in the sources between one state and the other state. The sources spend most of their time in the Lauhar state, so where the corona is very powerful. Then we observe jets. We think that the jets are produced by, as I mentioned at the beginning of the talk, by the slow evaporation of the corona by the rotating magnetic fields. And when the transition from the thermal dominated state to the power law state occurs, then is when these plasmoids are ejected, the superluminal components are ejected, so the transition seems to be a rather violent event. This is an illustration of the relation between the corona, that is represented by these dots around the black hole. The black hole is the black dot in the middle, and this is the accretion disk in the different states. We were talking about the low state and the high state, but there are other transitional states. So in the low state, we have the very powerful corona, but the accretion disk is truncated far away from the black hole, and because of this, the X-ray emission is not as strong, the soft X-ray emission is not as strong as in this state where the accretion disk goes all the way to the black hole. But now we still have this emission here at MeV energies, and this is very difficult to explain. It has been observed by different instruments, by COMTEL, OSI, BATSE, on the old Compton Observatory, and it has been observed more recently by the SPI instrument on board the Integral satellite. So what is the origin of this very, very high energy tail? It is not a thermal tail, because at MeV energies, the compact region in gamma rays is self-absorbed because of pair production. So there should be some other mechanism. So what I'm going to discuss very briefly is what happened if in this strongly magnetized, extremely hot corona, we inject a population of non-thermal particles. In that case, these particles, either electrons or protons, will interact with the different fields that we have in the corona. These fields are a very strong photon field, this X-ray emission I was talking about. Then we have a lot of matter because the density of the corona can be very high. And then we have very strong magnetic fields. So this is a very complex scenario. So the idea is to inject the relativistic particles and to calculate in this environment what is the radiative output in order to see whether we can explain the origin of this high energy tail. Now, there are two basic approaches to this problem. One is the Monte Carlo approach. This approach makes rather easy the treatment of the radiative processes by the photon statistic is poor. Essentially, we inject in a medium a particle, and we take into account all the interactions that this particle will suffer in this medium, and we follow the trajectory of the particle, and we count all photons that are produced during the movement of the particle. But we can repeat, we must repeat this process thousands of times, and this is a very consuming for computers process. There are several papers published using this approach, but now I want to talk about another approach that is a semi-analytic approach. It consists in solving all kinetic transport equations for all type of particles in the system. So here, photon statistic is not an issue. The real problem is to solve a very complex system of integral differential equations, taking into account all these interactions that occur. The first issue that we should fix is what is the configuration of this corona, this hot plasma around the black hole. There are several proposals. One is a rather steady corona, spherically symmetric around the black hole. Then in some systems, we could have an advection-dominated corona. Perhaps this is the situation in the black hole at the center of the galaxy, because we do not observe this type of excess of emission there. And there are other proposals as system, not an homogeneous corona, but a system of clamps and also flaring blobs. But the theoretical problems with these models are much stronger. They even have problems to reproduce the hard X-ray emission that we observe. So I will go, I will adopt the extended corona model, and I will fix my setup in something like this. The corona will be considered spherical, so we have a configuration that is the black hole in the middle, an accretion disk that essentially will be a Sakura-Sunayev accretion disk, and then we will have a spherical corona. Concerning the black hole, I will adopt this mass that is the best estimate available for the black hole mass in Cygnus X1, the best studied black hole candidate in our galaxy. The size of the corona seems to be something like 35 gravitational radii for this mass. This means something like 5 times 10 to the 7 centimeters. So we are talking about a very compact region. The luminosity of this corona is very well established from observations. So we know that it radiates X-rays at a luminosity that is 1% of the Eddington luminosity of the black hole. This means roughly 10 to the 37 erg per second in X-rays, in hard X-rays. The electron temperature, as I already mentioned, is 10 to the 9 Kelvin. Some models consider different temperature for the protons, but these models are more indicative for the advection dominated situation. So in the case of the calculations I'm going to show, I have used just temperature of 10 to the 9 Kelvin for the thermal material in the corona. The magnetic field should be at least in equipartition with the luminosity if you want to expel the jet by magnetic effects. The jet originally is Poynting dominated jet, so we need at least an energy density in the magnetic field similar to the energy density in the rest of the system, and this leads to high values for the magnetic field, several times 10 to the 5 Gauss. This is a critical point because synchrotron losses for particles are very, very strong with such a magnetic field. Concerning the particle density in the corona, is quite dense with a density of almost 6 times, more than 6 times 10 to the 13 particles per cubic centimeter. Well, so this is more or less the situation. We have a black hole, the accretion disk that penetrates a bit inside the corona. Otherwise, we should not have this quantum reflection feature and the iron K-alpha line. And this is the corona, the black hole is in the middle, and we have the donor star. We should not forget about the donor star, because if this is a massive star, then it will have a very strong photon field. And if we are going to produce gamma rays in this region, these photons can absorb the gamma rays by pair production. So we will take into account also the photon field produced by the star. I said that I will consider a static corona. This means that the escape of the relativistic particles from the corona is essentially by diffusion. The diffusion coefficient will be adopted here as the Bond diffusion coefficient. Our ignorance about the diffusion coefficient in the corona is almost complete. So this is the simplest assumption I can make. The photon distribution, energy distribution of the hard part of the corona is a power law, as you have seen in the previous pictures. And the index in the Lauhars state is well measured, is around 1.6. The cutoff energy for this power law is around 150 kilo electron volts. Concerning the photons coming from the disk, they will be thermal photons with a typical temperature of around 0.1 kilo electron volts. So, I will inject relativistic particles in here. Relativistic particles normally have a power law distribution. This is because we expect that the acceleration mechanism will be a diffusive acceleration mechanism. I will say a few words about the mechanism that accelerates these particles in a moment. We don't know what is the relation between the power injected in relativistic protons to the power injected in relativistic electrons. In a situation of equipartition, we will have equal power injected in both both species. So we introduce this parameter here, A, in the case A1, this means same power in both species. But in some occasions, we have reasons for thinking that acceleration mechanisms are more efficient for protons than for electrons. Radiative losses are not severe for protons. And for instance, in cosmic rays, we observe that most of the cosmic rays are formed by protons, not by electrons. So we will consider also a corona where the relativistic particles are mainly protons. This will be the case A equal 100. Now, in addition to the injection of these primary particles, by primary particles I mean particles that are locally accelerated in the corona up to relativistic energies, we will have the injection of secondary particles. These are particles that are produced in the corona by the interaction of the primary particles. And these particles will be charged pions that will be generated by proton-proton collisions. This is essentially hadronic and strong interaction. Then we'll have proton-photon interactions between relativistic protons and photons in the corona. And also neutron pions will be generated, that these neutron pions will decay yielding gamma rays. But the charged pions will decay yielding muons in the corona. A muon essentially is a heavy electron with a lifetime of 10 to the minus 6 seconds. So these particles in a magnetic field of 10 to the 5 Gauss can radiate a lot, and we should take into account this radiation in our calculations. And finally, when these particles decay, they inject electron-positron pairs. And also electron-positron pairs can be injected by other processes, like a Bethe-Heitler process. This is the creation of electron-positron pair in the electrostatic field of a nucleus, and photon-photon annihilation. This is pair creation by the annihilation of two photons, and this phenomenon will be quite common in a region as reaching photons as our corona. Well, a couple of words about how these relativistic particles can be accelerated. It's very difficult to have shocks in the corona to accelerate particles because we have this very strong magnetic field. So the plasma, from a mechanical point of view, is almost incompressible. But there is turbulence expected to be, we expect to have turbulence in this plasma and magnetic reconnection, not only at large scales, as we saw at the beginning of the talk, but also at smaller scales. So in a turbulent environment, the classical reconnection of magnetic field lines with opposite polarity can lead to the acceleration of particles that are trapped here and bounce several times between the approaching magnetic mirrors. There are simulations performed recently by Kowal, Lazarian, and others that seems to show that this phenomenon is quite efficient and in some sense can mimic diffusive shock acceleration. By this, I mean that this process can produce a parallel law distribution of relativistic particles. This is a simulation in 3D of what happened in one of these turbulent layers between converging magnetic mirrors. You see that some magnetic islands are formed. When particles are trapped in these islands, they bounce and get energy, and then they escape and are trapped in another one, and then we have acceleration. The acceleration efficiency, or the acceleration time scale, let's say, is proportional to the magnetic field, and there is an efficiency that is related with the reconnection velocity in the plasma. Now, normally this number is quite small, but here we have a very, very strong magnetic field, and this reconnection velocity is of the order of the Alfvén velocity, and since the Alfvén velocity is related with the magnetic field linearly, we can get this number quite high at the level of perhaps 1% or even more. These are simulations of what happened inside of one of these magnetic converging holes or mirrors we have in the corona. So here, for instance, you have how the particle bounces. This is the distance, and then it gains energy. Here you see the increase of the energy of the particle. The final result, when you inject a lot of particles in a system like this, is the generation of a power law that could extend up to very high energies. For protons, this could be TeV energies depending on the conditions. So now we are ready to calculate the losses for all these particles. Just to give you an idea of the complexity of the situation, for electron-positron pairs, we will have synchrotron losses in this very strong magnetic field. We will have inverse Compton losses against different type of photon fields. And then we will have Bremsstrahlung losses, relativistic Bremsstrahlung losses. And finally, we will have losses of electron and positron because they annihilate. And regarding protons and charged pions, we will have, again, synchrotron losses, and we will have proton or pion photon losses and proton-proton interactions or proton-pion interactions. Regarding muons, all the same losses that for electrons, because as I mentioned, muon essentially is a particle that is identically except by the math and the life. Yes, I imagine. Thank you. Well, so we have to solve the kinetic transport equation, and the steady state is something like this. This is the escape time for the particles. This is our injection, and this term is for the losses. For the photons, we have something like this with different type of injections that come from the different processes that produce photons in the corona. As you imagine, all these equations are coupled. This is the whole set of equations. We have one equation for each species of particles, and then we can go on and calculate the losses and the acceleration for each species, electrons, protons, pions, muons, to get the maximum energy in each case for each type of particle. And then once we have made all that and we have solved our equations, the issue is not finished, because we have this photon field coming from the star, the massive star, and this will absorb our photons. And so we need to calculate the opacity to gamma ray propagation in the photon field of the companion star, and this system is of course not stationary. It's in a steady state because it's binary. So we need to calculate the absorption coefficient that is here against the energy, and also at each position of the orbital phase of the system. So you can see that we have almost complete suppression of emission above a few giga electron volts up to TeV electron volts for most of the orbit. So if we go directly to the results, this is the excess of gamma rays that we were trying to explain. This is our model with equal number of electrons as protons, and this is the thermal emission, this is the non-thermal component, and you see the suppression in the Fermi range, GeV energies of the emission because of the absorption in the companion star. And a prediction for this from this model is that at high energies, where absorption is not anymore an issue, we will have a strong emission that could be, in principle, detected by future instruments like CTA, the Cherenkov Telescope Array. By the way, there is a chance for the North Array to come here, to Mexico, to San Pedro Marte. This is the same. We can get a nice fit also in the case of dominance of protons, but then the feature at high energies is higher. So with CTA observations, we could conclude something about the number of protons in our system. And just to finish, every system with strong magnetic fields and turbulence produce flares, so we should face also the situation that is beyond the steady state, and we can also study flares injecting a variable population of particles, but now equations are far more complicated. We have this dependence with time, and we have this term. So we have calculated what happened during one of these flares, and this is for Cygnus X1. So you see that there's a significant variation at MEV energies, and also a very strong variation of about 1 order of magnitude at TeV energies that is currently outside from our range of observations. But hopefully in the next few years we will be able to detect these flares. And just to finish, because I think my time is going out, I want to mention that a byproduct of this hadronic interactions we have inside the corona is the production of neutrinos. This is just the composition of the spectral energy distribution from one of these sources, the different components. So you see we have different types of components. The spectrum actually is quite complex. We have contributions from proton-photon, proton-proton interactions, and from these interactions neutrinos are produced. And the neutrino emission might be detectable in some cases if the flare is very long. For instance, this is a calculation of the neutrino output of this particular system. Here you have the predictions of the model for the neutrino emission during the flare compared with the detection flux, the discovery flux for the source. So if the flare lasts around 80 days, it would be possible, in principle, to detect with instruments like IceCube, this huge neutrino detector in the Antarctica. So my conclusions are this. I have very briefly presented what I consider a consistent treatment of the non-thermal processes in a strongly magnetized corona. I have solved a set of coupled differential equations for all type of particles, transients or primary particles. We have applied this method to Cygnus X1 and other sources, and we get a very reasonable fit of this excess of gamma rays that is observed, and we predict also some radiation that is not observed. And finally, the methods I have presented here can be used for other systems where we have also strong magnetic fields and strong photon fields, like, for instance, long gamma ray bursts. So since the chairman is standing here, I think it's time to finish. Thank you very much for your kind attention.
Yeah, at the beginning of your talk, you asked a rhetorical question, which is what does this subject have to do with star formation? And you said it's because stars sometimes die and leave black holes. I would suggest there's a much closer connection. That is, when stars are born, we see very much the same phenomenon. We have many of the same questions. You know, what are the kind of phenomena related to magnetic fields in the disk and how they interact with the magnetic fields of the central object. The main difference is that in these black holes, there are many interesting relativistic high energy processes. The plasma around stars, young stars, is incompletely ionized. And so we have a huge advantage. We have line radiation.
Yes.
But otherwise, I think in the general context, the two fields are really very close.
I completely agree. Actually, one of the reasons I am here is because I am working with Luis Felipe and Abel Araudo precisely in this kind of things. If you have a protostar that is forming, you have an accretion disk, and you have these jets. These are not relativistic jets, but we can know very well the velocity of this jet because, as you mentioned, we can measure the lines, and these jets at some point are stopped in the molecular cloud or in the terrestrial medium. Shocks are formed, particles are accelerated, and we observe in some of these objects non-thermal emission at radio. Very interesting, Luis Felipe, Carrasco, and others have detected, for instance, linear polarization in the innermost part of the jet of HH81, a very famous massive protostar with jets. And the presence of these relativistic electrons in there, I think, is a guarantee that we should observe some gamma rays. Why? Because we have relativistic particles and we have an environment with a very high infrared field. So inverse quantum scattering of the infrared photon is unavoidable. So I think that at gamma rays, a new window is being opened, a window to study, as you say, star-forming processes and protostars in this kind of phenomena.
So I was a bit shocked by the amount of ingredients your model has. I'm just wondering whether you are using or you are solving these equations on top of a black hole background space-time.
The short answer, or the long answer? The short. Well, we are using, it depends. If we go to a gamma ray burst, I will use not the equation, I have this for sure. I will use other things with relativistic effects taken into account. But for a microquasar, it's not necessary. So space-time in these calculations is flat.